Welcome to BMM4113, Advanced Materials Characterization Theories and Tools. This video is Lecture 4 on X-ray diffraction, prepared by Associate Professor T.S. Dr. Siti Rabiatul Aisha Binti Idris. We will cover the content for X-ray diffraction, starting with the introduction to X-rays and XRD, history, principle of XRD, interference and diffraction, basics of crystallography, XRD components and working, sample preparation, and finally, XRD analysis. The learning objectives of this lecture are to gain a fundamental comprehension of X-ray diffraction, including the principles of light interference and diffraction, and the basics of crystallography. Our journey begins with the Blueprint of Matter, a visual guide to X-ray diffraction, exploring the journey of an X-ray from wave physics to atomic lattices. This video serves as a self-guided visual reference handbook for materials characterization. The core insight is that for measuring atomic structures, the tool must match the scale of the target. X-rays possess the exact wavelength required to interact with crystalline atomic planes, enabling non-destructive analysis and rapid phase identification. X-rays are generated using the lab standard, an X-ray tube, or the absolute limit, a synchrotron. The X-ray tube uses high-energy electrons striking a metal anode, while a synchrotron accelerates electrons to near-light speed for an intense, highly coherent beam. Diffraction involves the interference engine. Constructive interference, or diffraction, occurs when waves are in phase, reinforcing each other to produce strong, diffracted beams. Destructive interference, or silence, happens when out-of-phase waves cancel each other out, creating the dark background. The target of X-ray diffraction is the crystal structures matrix, including body-centered cubic, face-centered cubic, and hexagonal close-packed structures. The regular arrangement of atoms allows the X-ray to act as a diffracting wave. Mapping the crystal uses Miller indices. Directions UVW are specific directional vectors. Planes, HKL, are the atomic surfaces the X-rays reflect against, calculated by taking the reciprocal of the axis intercepts. Note the difference in notation between single planes and families of planes. The defining moment is Bragg's law, n lambda equals 2d sine theta. For diffraction to occur, the extra distance traveled by the lower wave, 2d sine theta, must be an exact multiple of the wavelength, n lambda, otherwise destructive interference flatlines the signal. The diffractometer has a mechanical flow architecture consisting of 5 main components: the source, incident beam optics, the sample, diffracted beam optics, and the detector. The system configuration dictates how the source, sample, and detector move relative to each other. Beam control sculpts the X-ray beam using Solar slits to limit axial divergence and receiving slits to control the physical footprint, and filters, like the nickel filter for K-beta stripping, to clean the signal and ensure monochromatic K-alpha beam reaches the detector. Detector technology has evolved from 0D scintillation detectors requiring slow physical scanning to 1D position-sensitive detectors measuring a large 2 theta range simultaneously, and finally 2D area detectors like GADs, which capture large 2 theta and chi ranges instantly with very short measuring times. Proper sample preparation is crucial. For powder preparation, particle size must be between 0.1 micrometers and 40 micrometers to avoid artificial peak broadening or pore statistics. Bulk preparation requires a perfectly smooth, heavily polished flat surface, and thermal annealing may be necessary to eliminate surface deformation. The diagnostic rulebook details the rules of reflection, showing which atomic planes are permitted to reflect against. This includes simple cubic, body-centered cubic, and face-centered cubic structures, allowing us to deduce the fundamental Bravais lattice of an unknown sample, effectively creating a structural fingerprint. The strain spectrum illustrates how defects impact data output. No strain results in a sharp, centralized peak. Uniform strain causes the peak to shift to higher angles, but the shape remains sharp. Non-uniform strain, or RMS strain, causes the peak to broaden significantly. Decoding the diffractogram links the graph to the atom. Peak position determines unit cell dimensions. Peak intensity determines phase quantity and atom types. Peak width determines crystallite size and non-uniform microstrain. Peak shift determines macrostrain. The power of XRD includes rapid identification of crystalline phases, completely non-destructive analysis, determination of precise lattice parameters, and accurate measurement of thin film thickness. However, it struggles with amorphous materials, has detection limits around 3%, and zero spatial resolution. XRD remains the definitive tool for uncovering the periodic blueprints of matter. For additional information and further reading, these lists of resources, including documents and video links, can be referred to. In summary, X-ray diffraction is highly useful for characterizing materials, providing information on phase analysis, lattice parameters, strain, texture, and more. Choosing the correct method type is critical. It is a powerful technique, especially for thin film characterization. Thank you for your attention. This concludes the video on X-ray diffraction.